And the thing I wanted to pull up, which is not there, is this. Where's the more tools? More tools. Clock. Clock. And we'll put that over there and shrink it. There we go. So we get these long silences on the video, but you'll be able to see that the clock is going. It's actually, it isn't that it's like nothing's happening. No, something's happening. You'll see that that's going, we're going. Okay, so inequalities. By inequalities, we mean greater than or equal to, less than or equal to. Right? It's the bar underneath that says or equal to. There's actually one other inequality. Do you know what that is? The one other, which we won't mess with here, but the other one would be not equal to. You can say something is not equal to something else. But we're just dealing with these four right here. So again, there's usually, out of a class like this, a few that are still not really that comfortable with these symbols. But you know, it's the pointy end of the symbol is towards the smaller thing. Right? The pointy end is towards the smaller thing. I don't know whether you're using alligators and things like that to remember that. If you say x is greater than 4, when you graph it, obviously you got to have a 4 on there. Right? Greater than 4 means 4 itself does not solve that inequality. Right? If I said 4 is greater than 4, that would be false. So 4 is not part of the solution. So we would make an open circle on 4 to indicate not part of the solution. Right? The shading is always an endpoint, open or closed, and shading. The shading is the x. In this case, since x is greater than 4, greater than on the number line means to the right. So the shading is here. I mean, if you wrote it in the order that it is right here, you would say, here's the 4, and the x is here. And because the number line always, that would be the symbol, because greater is on the right, it looks like 4 is less than x. But 4 is less than x, and x is greater than 4. It's the same thing. It's kind of like our symmetric property with an equation. You could flip the sides, and it would be true. Right? Now, the greater than or equal to, the only difference is shade in the point. Because now if I said 4 is greater than or equal to 4, you would say sure. Right? 4 solves that inequality. So color in the point, the end point, so that it's clear that point is part of the solution. X is less than 4. Okay, here's the 4. X, the shading, is to the left. And as always, the symbol goes like that. Right? Because on the number line, to the left is less. And the only difference between these two, color in the dot. I know that's review for you. Good. Good. Great. Sophia? Christian? You okay? Let me know if I go too fast. Now, when we solved equations, we did it by applying properties of equality. The thing is, we're going to apply properties of inequality, which are pretty much the same as the properties of equality. You know, if for an inequality, we still, in order to isolate the variable on one side, we will do operations to both sides. just make sure whatever you do to one side, you do to the other side. And there is a table in the book that shows that, but I mean, this is the summary of it. Whatever you do to one side, do to the other. And it will work the same except for two exceptions, which I'll show you on the next slide. Okay, let's see. Mitchell, not here. And that's not here. Not here. And Weathers, sorry, I gotta take this. Okay, does everybody get it? Do you remember what's the one difference when you're solving an inequality? Something to do with if you multiply, remember when you multiply or divide by a negative, you got to flip the inequality sign. That's different. Right. And the reason is, I mean, when you're talking about positive numbers, right, the numbers are getting bigger as you go to the right, so 2 is less than 3. But in terms of negative numbers, since it's getting bigger as I go to the left, -2 is actually greater than -3. Right? They flip their respective positions there when you multiply or divide by a negative. So that's one thing that we have to keep in mind, right? When we're doing operations to both sides, if you come up with a place where you're going to multiply or divide by a negative, you've got to flip that symbol. Good? Jaden, you okay? So here would be an example. Solve and graph. So we're going to do operations to both sides, the same as we did with equations, until we've isolated the variable on one side. And then the answer will be the inequality symbol plus the number that's on the other side. Remember, first, before we start adding things to both sides, we need to simplify everything we can on the same side. And there is something we could do to simplify, isn't there? Distribute first, right? We need to do this. That's -6x plus 15 plus 1 is greater than or equal to 4. You see how the negative 3 times negative 5 makes positive 15? Okay. And then we have some like terms on that same side. Which are they? The 15 and the 1, right? We need to put those together. That's negative 6x plus 16 is greater than or equal to 4. Okay, now we've got the variable all in one term. That's good. Now we need to move the constant so that variable term is alone, right? So subtract 16. Negative 6x is greater than or equal to, that's a bad, try that again. Negative 16 is greater than or equal to negative 12. Last step, divide by negative 6, which means I have to flip the sign, right? That's going to change this greater than or equal to a less than or equal to. And because, in fact, the minute if I go like this and I multiply by or divide by negative 6, at that moment, this is wrong. I've got to like change the symbol or erase the symbol. I'm going to do it over here. I'm going to write negative 6x divided by negative 6 greater than, now it's less than or equal to negative 12 over negative 6. Right? At the moment I divide by that, I got to flip the symbol. Okay, on the left, the negative 6's cancel. What's negative 12 over negative 6? Dos. X is less than or equal to 2. Okay, the graph, it says solve and graph. I mean, there's only one number you got to put on the graph. That's the 2. I mean, I don't care about writing a whole bunch of numbers to the left and the right. The whole thing really depends on how you deal with 2. So here's the 2. Should I use open or closed circle on 2? Because the or equal to, you're going to use closed. Okay? Remember now, the X represents the shading. X is less than or equal to 2. The shading is less than, which means to the left of 2. So which side do I shade? Here. Right. Solve and graph. Sophia, you okay? Okay, try that one. Random. Oh, I didn't get that one either. All right. If you got an answer, raise your hand. Let me see. You get the number? Looks like you do. Yeah, if you remember, you can grab your calculator on your way in. Every day, grab it. What are you trying to do? going to add 16? Or negative 2 times 9 is negative 18. Yeah. Yeah. Is that a negative? I'm seeing some right answers here. Over negative 2, negative 8. Did you get it? Yeah, I'm seeing the same common mistake. What's 16 divided by negative 2? Negative 8. Right? Good. Sorry. You're good. Mostly pretty good. Right, so everything worked the same as solving an equation, right? Operations to both sides. The main thing being, because I divided by negative 2, I flipped the symbol from greater than to less than. And then when I graph it, right, I can put negative 8 right in the middle, open or closed, closed, left or right, to the left. Good. We're good, Madison E? Right, Justine? Come on. Now, here's an inequality. I want to show you this, right? Because this gets into why, when we solve equations even, we always say, move the variable terms to the side where you have the bigger one. Move the smaller term, right? Okay, let's see. Okay. Notice what would happen. This is the same thing written twice. Notice what would happen if I didn't move the smaller variable term. Right? In this case, which is the smaller variable term? Negative 3y or positive 2y? The smaller would be negative 3y. But what if instead I said minus 2y? Minus 2y. I mean, that's okay. You could do any of those move any of those 4 terms as the first step. That would be all right. But if you move to the wrong side, at this step here now, negative 18 minus 5y is greater than or equal to 52. I just created a situation where I'm going to have to remember about that flipping of the sign. Right? If I was careful, and instead of that, I added 3y to both sides, negative 18 greater than or equal to 5y plus 52. You know, now I've got a positive coefficient in front of the variable. I will not have that same issue. Right? So that's why we always recommend move the smaller of the variable terms to the other side, because then you're sure that it's positive. What you've got to be a positive variable term. If you don't, you just got to remember, you know, add 18, divide by negative 5, flip the symbol. Subtract 52, divide by 5. Don't worry about flipping the symbol. Okay. Okay, try this one. See, I got everybody else. If you did everything right, you should be probably running into trouble here. Did anybody get all the variables to cancel? And if you remember when we solved equations, that happened, right? We had two situations. When the variable cancels and you're left with a false statement, it means no solution. If the variable cancels and you're left with a true statement, it means solution's all real numbers. Anything you want to plug in is fine. Well, we have the same situation with inequalities. If I multiply this, distribute, negative 6x minus 2 is greater than negative 6x plus 7. Right? I add 6x. And I'm left with a statement which is negative 2 is greater than 7. Right? Which does not depend on the variable. There are none. And it happens to be false. So what does that tell you? No solution. Right? This is never true. This is never true. No solution. Right? That, if you get to that, it doesn't mean you did something wrong. It means there's no solution. You could have done everything right. Of course, then there's the flip side of that. Right? Distribute. 10x minus 15 minus 7x is less than or equal to 3x plus 8. I combine like terms. Let's see. 3x minus 15 is less than or equal to 3x plus 8. Right? That's these two terms here. And then subtract 3x from both sides. I get negative 15 is less than or equal to 8. Which, again, no variables, so it does not depend on x, happens to be true. That means it's always true. Any x you plug in, the statement is true. So, solution is all reals. The book uses a slightly different language, which is this. And when you're doing the homework, you're going to have some problems like that. They're going to give you some equations like that. And they're going to say whether or not this thing is always true, never true, sometimes true. That's the always true. That's the never true. And something like that is the sometimes true, right? It's true for this particular condition. It's true. It's not always true, but it's sometimes true. All right, a compound inequality is when you've got two inequalities, and they're connected by the words either and or. Right? If they're connected with the word and, it means in order for the compound inequality, this whole thing, to be true, then both of those statements must be true. Now, if you look at, if we graph these, right, x greater than negative 1. Should I make that open or closed circle? It's an open circle, right? I probably got too big of a... There's my open circle on negative 1. Should I shade it to the right or to the left? If x, the shading, is greater than, on the number line, that means to the right. All right, so I'm going to shade this one that way. All right, how about the x less than 3? Is the 3 open or closed circle? It's open, right? And is the shading to the right or to the left? Right? The shading is x less than, so it is that way. Now, in order for the compound inequality, the whole thing to be true, then both of those statements must be true. Now, where do those two lines overlap? In between which two numbers? Between the -1 and the 3, you got both lines, right? So that's where this thing is true. So you would say the solution is everything in between -1 and 3, not including the -1 and the 3. You could say another way to say this. You could say, here's -1 is there, 3 is there, the shading is in the middle, and use your symbols, less than, less than. It's a three-part inequality. -1 is less than x is less than 3. That's the solution. On the graph, if you were going to graph it, you'd have to some way indicate, I mean to say, only this here, right? This part is not in the solution. This part is not in the solution. Right, so compound and both true. All right, now we look at the other one. When you connect with an or, actually only one of them has to be true in order to solve the whole thing. Right? In order to solve the whole compound inequality, we just need one of those statements to be true. So let me do the same thing. X less than -1 would be open circle here. That didn't work. Open circle here, shaded to this side. X greater than 3 would be open circle here, shaded to that side. So the solution on the graph, it's both that piece of the graph and that piece of the graph, right? If x is over here, it solves the whole thing. If x is over here, it solves the whole thing. Is there any place on the graph where both are true? No. I mean, if that was an and, there would be no solution because there's no place they overlap. That's a typical what an or looks like. You know, two different places on the graph. And you know, how do you write that? I mean, you have to write it just like that. X is less than -1 or x is greater than 3. And that's what the graph looks like. Okay, let me write it here. So I should say at least one is true. That's what the or means. I mean, if this one on the left had been an or, then what would have been the solution to the compound inequality? Well, let's see. This part of the number line is covered by that. This part of the number line is covered by that. The middle is covered by both. All real numbers. Everywhere on the graph there, at least one of them is true. So if that had been an or, you would have said no, all real numbers. If this had been an and, you would have said no solution because they don't overlap. And so when you get a compound inequality like this to solve, then you got to solve both inequalities, right? Just like we did already, right? We already know about solving inequalities, so just do it twice, right? This one, what should I do? Add 1. So 6 is less than 3x. Divide by 3. So we get 2 is less than x. How about this one? Divide by 2. All right, therefore, x is less than 6. So let me fatten up my pen again. So Okay, so 2 is less than x, so here's the 2, open circle, shaded this way. X is less than 6, open circle, shaded this way. Right. Since an and, it's true where both of them are true. Where are both true? In between which two numbers? 2 and 6, right? So I'm going to shade that in like this. There's my solution. And again, you can write that as a 3-part inequality. You would write it like this. 2 is less than x is less than 6. Right? That when you see a 3-part inequality, it is an and. You don't see the word and, but it's an and. It implies that it's both greater than 2 and less than 6. So there's an implied and. Okay, and then here's an or. Solve them both. Subtract 1, subtract 1. 15 is less than 5x. Divide 5, divide 5. 3 is less than x. Right? Subtract 9. 3x is less than negative 3. Okay, what do I have to do with this next step for that 1? Divide 3. Do I need to flip the sign? Do I need to flip the inequality sign this time? No, because I'm dividing by a positive 3. Don't get confused with, like, there are negatives involved, but it's not what you're dividing by. So do this. Divide 3, divide 3. So x is less than negative 1. So fatten that up. So 3 is less than x. X is greater than 3. That would be open circle, shade to the right. Oops. X is less than negative 1. Open circle, shade to the left. And that is the graph. Because it's an or, you've got 2 disconnected parts of the graph. That's okay. Altogether, this area and this area make up the solution. And if you're just going to write it, right, not draw it, but write it, you would have to write it like this. You would say, x is greater than 3, or x is less than negative 1. Something like that. Just got to make sure you use the or. You started with an or, it's still an or. Okay. So good. That's it. So the homework is here. And again, next class, we'll do a quiz over the 1, 2, 1, 3, and 1, 4, which was real numbers, expressions, solving equations.